Welcome to the presentation of our paper, an automated rapid test for viral nanoparticles based on spatiotemporal deep learning. My name is Konstantin Wüstefeld, and I'm from the Computer Graphics Lab at TU Dortmund University. At this place, I want to thank the SFB 876 for funding our project and the Leibniz Institute for Analytical Sciences for handling the biological and chemical concerns of the sensor. At the moment, the motivation for work is very easy to comprehend. Over the past years, we saw an increasing frequency of emerging infections like the current COVID-19 disease. An increasing amount of worldwide travel takes place so that a virus can travel over long distances in a very short time. There are also big social gatherings which can turn out to be superspreading events of an infection. This has to be avoided. So our goal is to provide a device which can be used as a rapid test on site. To reach this goal, there may only be few parameters for user interaction, so that also a non-expert can use it. It should also be affordable for mass tests, so that we want to test many people in a short period of time in order not to block the whole waiting queue in front of, for example, an airport or a stadium. A device which can accomplish this task is the PAMONO sensor, where PAMONO stands for Plasmon-Assisted Microscopy of Nanoparticles. On the left side of the slide, you can see the schematic setup of the sensor. In the middle of it, there is a gold plate which is coated by immobilized specific antibodies, which means that the antibodies bind to one specific type of viral particles. On the upper side of the gold plate, it is embedded in a flow cell with a liquid possibly containing viral particles being pumped over it. On the lower side, the gold plate is lighted by a laser beam in the so-called resonance angle. In this configuration, and with no particle attached to the antibody layer, the reflected laser beam can be recorded in the form of a weak and static signal. As soon as a particle attaches to the antibody coating, it changes the reflection conditions of the gold plate at the place of attachment. This light change results in a bright spot on the recorded images. On the right side of the slide, you can see a photo of the actual device, which is quite similar to the schematic setup. The only thing which is added here are the mirrors which basically enable a more compact construction of the sensor. As the name of the sensor already says, the effect that is used here is the plasmon resonance, which enables us to record particles which are currently of sizes between 80 and 200 nanometers. For measuring results, we use synthetic and virus-like particles, as they can be received easily in well-defined sizes. Due to the simplicity of the device, the components are rather cheap, while the whole construction that you see in the photo has only the size of a suitcase. After we saw how the images of the PAMONO sensor are recorded, we now come to the automatic detection pipeline, which recognizes attaching particles based on spatiotemporal deep learning. At first, we preprocess the images to see the particle regions more clearly. For this purpose, we make use of the advantages of two different preprocessing variants, and we will see why this makes sense. After that, we will use one preprocessing image stream for the generation of spatial candidates, and the other for checking the spatial candidates from a temporal point of view. The last step is the connection of single particle regions in consecutive frames to one particle trace. At the end, we will receive a series of regions for each attached particle. Now we will look at the preprocessing variants. The recording you can now see is a cutout of the raw image stream, so this is the bare signal perceived by the camera. We can see in the plot above that we cannot distinguish directly between a virus signal and a noise signal. The reason for that is a very strong but rather static background signal. This background can then be removed with a global preprocessing, so that we can see the typical step function representing an attaching particle. As the particles of interest stay attached to the sensor surface all the time, it is becoming more and more complicated to recognize new attaching particles next to already attached ones. While this is a problem for the spatial detection in the globally preprocessed image stream, we can solve this with a local preprocessing, which utilizes a sliding window method to make attaching particles disappear again as they become part of the local background over time. Because we use the locally preprocessing images for proposing spatial candidates, We also apply a dynamic contrast enhancement in order to receive a high recall in the spatial prediction network. Now we come to the spatial prediction network. This network has the task to propose regions that look like particles of interest. It returns three values: a pixel mask that marks all the pixels belonging to a proposed region, a bounding box around it, and a confidence score. As the mask RCNN provides all this information and has shown to be capable of solving the detection problem on natural as well as medical images, we choose this as our spatial predictor. As a backbone, we use the ResNet50 feature pyramid network, which was pre-trained on the natural images of the Microsoft COCO dataset and just fine-tuned it to our detection task. As we now have the spatial prediction and the globally preprocessed images available, we can check if the predictions are caused by a particle of interest, or just by a dust particle or another disturbance. So, as its input, the temporal filter makes use of the predicted masks and the bounding boxes around them. At first, we calculate the mean pixel value within the masked region, and the same for the pixels in the bounding box. When we then divide the particle value by the background value, we can get rid of the influence caused by deviations in the local background. A last preparation step is the normalization of feature vectors containing the relative particle signals. By this, we receive values which are independent of the particle sizes, which are reflected in the absolute heights of the step curve. Instead, we want to concentrate on the relative form of the feature series. Having generalized the time features, they are analyzed in a simple neural network consisting of 3 fully connected layers and a leaky relo activation function after the first 2 layers. The output of the network is a temporal classification of the proposed spatial regions. Before the last module of our detection pipeline takes place, we only have the information on where particle regions appear for each single image, but there is no connection between them yet. The trace generator provides this information by looking at the bounding box positions over time. In a bit more detail, we can connect 2 boxes which have a high spatial overlap and can be found in temporal proximity to each other. The reason why we do not only look at the very frame before and the very frame after the current one is that there can be small gaps within a long series of detected boxes. We connect all the boxes which have a spatiotemporal similarity to each other and call these series of similar regions particle traces. All particle traces that are very short are filtered out at the end, and the remaining traces are seen as actual particles. The short traces are seen just as dust particles or other disturbances. At this point, we can make use of the complete detection pipeline and visualize some of the results. In the upper video, you can see the detections made on a sample with a high concentration of particles. The lower video contains a sample with only few particles and some wave-like artifacts. In both recordings, we can see some temporal differences in the brightness of the images, which can also cause shortly missing or wrong detections. All in all, the results look quite good and show that we can compensate some of the disturbances. After a short visual demonstration, we now also have a look at quantitative results. Our tests were performed on an NVIDIA RTX 2070, which is a home user graphics card and already available in laptop computers. In the tests, we used particle sizes of 80, 100 and 200 nanometers, partially in mixed samples. While we can see the first detections after seconds, the pipeline reaches an average count exactness of 87%. As one could expect, the detection becomes harder for lower particle sizes and for heavier disturbances. A factor which is also very interesting for a rapid test is the separation of contaminated and non-contaminated samples. As we can see on the right side, we also detect a small number of particles in samples which do not contain actual particles. But we can also see that the detection count is much higher for samples containing particles. This also holds for the sample with the lowest concentration of particles in our test sets. so there's a clear separation between contaminated and non-contaminated samples. Coming to the end of the presentation, I want to give you a short idea of our future research plans. One thing is of course the evaluation of SARS-CoV-2 particles, which appear in ranges between 60 and 140 nanometers and therefore should be detectable with a PAMONO sensor. As we saw in the results of the detection pipeline, we get problems with increasing disturbances. With the goal of using the PAMONO sensor in the real world, which means at places with heavier external influence than in a laboratory, we are also working on methods for higher tolerance against disturbances. A third part of our schedule is a higher mobility of our calculation platform, which can be achieved by computation offloading or lighter neural network modules deployed on embedded systems. Thank you for your attention and your interest in our research. Goodbye.